So here's a scatter diagram. Do you all know what it represents? So here's the scatter diagram. Do you all know what what it represents? I see the numbers and colors, but what does this diagram really tell us? I see numbers and colors. What does this diagram really tell us? What does this diagram really tell us? Good question. This is a scatter diagram. It shows the relationship between the wave height, wave period, and frequency of each combination. It shows the relationship between the wave period and wave height and number of occurrences, probability of occurrences, the frequency of each combination. It's based on the real wave measurements. It's based on the real wave measurements. What kind of measurements? How do we get this data? The question is that what kind of measurements and how do we get this data? We use a wave rider buoys to measure these waves. These buoys float on the sea and recording the wave height and the time between the waves. I see two axes, wave height and wave period. I see two axes, wave height and wave period. What does this mean exactly? Wave height is the distance between the distance from the wave crest to wave trough. It's the distance between the wave crest to wave trough. This is the trough. This is the crest. This is the distance. That distance is called wave height. Okay, wave period is the time between two wave crest passing a fixed point. How much time it takes to complete one cycle. That's the time period. How do we decide what's the normal wave height and wave period? Let's see here. How do we decide what's the normal wave height and wave period? You see here 2 to 8 or 10 seconds and 0 to 1 meter. These are the more common. How do we decide what are the most common? Between these, from 2 seconds to 10 seconds and 1 meter to 4 meter, this is going to be the common wave heights, right? This is how we can come to know, like, how do we decide what's the normal wave height and wave period. What's the magic of the scatter diagram? That's what the magic of the scatter diagram. It helps us see most common wave heights and periods over a period, usually 1 year. Usually in a year, it helps us to see what's the most common. That helps us to see. It helps us to see what's the most common wave heights and periods over a period of time. That's usually 1 year. It shows us the waves we expect most often. So we can come to know, like, what are the waves we can expect most often. What are the waves we can expect most often? And the number tells us how common they are. This number tells how common they are. This number tells how common they are. This 2 to 3, 0 to 1 meter is quite common. These numbers tell us how common they are. And exactly, the more frequent wave conditions, the higher the number of in that section of the diagram. You see, this is the more frequent. This is going to be the more frequent, 2 to 3 seconds to 0 to 1 meter. That's going to be more frequent. That's why the number is higher. The number of occurrence, the number in that section is diagram is higher. What about the directions? How does that affect the diagram? You see here, this is from 0 degree, this is 30 degree, like that for each degree, each sector we have the data. A good point, wave comes from different directions. Wave comes from, we have 360 degree, like wave can come from any direction. Wave comes from different directions. Right, so we divide the ocean into sectors, like usually 12 sectors, each covering 30 degrees. So this helps us understand where the most of the wave energy comes from. So that helps us understand where, for example, this is the most of wave energy comes from which direction, which sector most of the wave energy comes from. That we can understand. So this helps us to understand where the most of the wave energy comes from. So if the structure is facing west, and we should care more about the waves from west. If the structure is facing west, suppose if the structure is like this, and we have to care more about the waves coming from west, so we have to orient in other way. Like if the structure is oriented like this, it will be more stiff in this direction. That's why the orientation of structure also matters based on the wave data. The direction, exactly, the direction matters a lot for structural design. So what do you mean by that? The direction matters a lot. Direction matters a lot for the structural design. We adjust the data to match the orientation of structure. So we adjust the structure to match the orientation of the we are just worrying as a structure to match the data, right? So, but there are so many different wave combinations. How do we deal with all these values? There could be a different combination. How do we deal with all these values? How do we deal with all these values? There could be a different combination, right? Great question, Daniel. We reduce the data. Instead of looking at all the 784 combinations, we focus on the mean wave height and mean period for each wave height range. We don't simulate all the combinations. We just pick a few key ones. We just give that representative conditions. So we can pick the representative conditions. We just pick the few key ones. We don't simulate all the combinations. We don't simulate all the combinations. We just pick the key ones. We pick the representative ones. This makes solution much faster. We still get accurate results. That makes us to get the solution much faster, but we still get the accurate results. How does the data help us design a structure? There's a question like, how does this data help us design a structure? Isn't just numbers on chart? No. Well, this data tells us about the typical C conditions. It helps us design structure to survive the most common waves and also able to withstand the rare extreme waves. So we are designing the structure that could withstand the most common waves, as well as it should withstand the rare extreme events, and we can use this to calculate how often certain waves will hit. We can use this to calculate how often the structure will get certain waves, how often certain waves will hit, how the structure will respond. Alright, exactly. With the scalar diagram, we can simulate how the structure will react to both regular and extreme wave conditions. We can simulate how the structure will respond to both rare as well as regular as well as extreme wave conditions. So wait. So we are using the real data to make decisions. What are we using? We are using the real data to make decisions. Does that mean the C can surprise us? Yes, the C is always unpredictable, but with the scatter diagrams, we can plan for the most likely ways. C is always unpredictable, but with this scatter diagram, we can plan for the most likely. We can plan for what? We can plan for most likely ways. With this scatter diagram, we can plan for most likely ways and still be prepared for the unexpected. So this scatter diagram gives us a clear picture of how the C behaves. So scatter diagram gives us which data gives us to get the clear picture of the C, how C behaves. Scatter diagram gives us a clear picture of how the C behaves, and with that information we design better, safer structures. So with what information? With the scatter data information, we design this structure safer and better. Yeah, exactly. The more we understand the waves, better we can design to protect the structures against them.